Hi everyone. In the last class, we have discussed about spectral properties of an element in a Banach algebra. In particular, we have proved the spectral mapping theorem. So today we are going to discuss about the spectral radius formula for an element in a Banach algebra. Okay, so let us quickly recall what is the spectral radius means. So if we start with a unitar complex Banach algebra, and A is an element of A. So we have defined spectral radius of A is nothing but supreme of mod lambda in the spectrum of A. Okay, so this is the radius of the smallest ball which includes the spectrum of A. So if you take any lambda whose modulus is bigger than spectral radius of A, if lambda is in C with mod lambda is bigger than spectral radius of A, then we can conclude that lambda is in the resolvent of A, or we can say that A minus lambda into 1 is invertible. And we also have observed that spectral radius is always less than or equal to norm of A. Okay. So now we can ask the question, how to compute the spectral radius of a given element? One way is to look at the spectrum, find the spectrum and look at the supreme of mod lambda in the spectrum of A. But that may not be convenient all the time. So for this purpose, we prove a result called the spectral radius formula. The spectral radius formula. It says that if A is in A, then the spectral radius of A can be computed using this limit n tends to infinity norm of A power n whole power 1 by n. So this is also nothing but infimum of that means by looking at the iterates of A, we can find out the spectral radius formula. So to prove this result, we need one lemma. So let us quickly prove this. Let X be a Banach space and B be a subset of X. You can say that then B is bounded if and only if phi of B is bounded for every phi in the dual space of X. So let us try to prove this result. Here one way is trivial, that when B is bounded and phi is element of X star, phi of B is bounded. So B is bounded implies phi of B is bounded for all phi in X star. This follows by the definition of boundary linear functional. It maps bounded sets into bounded sets. On the other hand, let us assume that phi of B is bounded for every phi in X star. So let us pick up some element. Let us take x in x, x in b. Let us take x in b. So define a functional from x star into c by ex at phi by phi of x for every phi in x star. So this functional is known as the evaluational functional. Okay, now we want to show that ex is bounded. So we have norm of ex norm phi into norm x, and in fact if you want to look at norm of ex as a functional, this is supreme of norm ex at phi, where phi is coming from x star, and norm phi less than or equal to 1. This is supreme of mod phi of x, where phi is coming from x star and norm phi less than or equal to 1. So this is exactly norm x. So by a consequence of the Hanbanach theorem. Okay, so there exists a functional phi such that norm phi x equal to norm x. So by that result we can conclude that norm ex equal to norm x. That means this ex, this set is bounded. This is pointwise bounded subset of so ex is from x star, so x double star. So we can conclude that by the uniform boundedness principle, this set is uniformly bounded. Is bounded. So that is there exists some m such that norm of ex is less than or equal to m for every x in b. So this implies norm of x is less than or equal to m for every x in b. That means we can conclude that therefore b is bounded. Okay. So this second condition, that means phi of b is bounded for every phi in x star. So this condition is known as weakly bounded property. We say that b is weakly bounded if and only phi of b is bounded for every phi in x star. So what we have shown is that b is bounded if and only if b is weakly bounded. Okay, now using this result we want to prove the spectral radius formula. So let us look at the proof of the spectral radius formula. So we want to show that spectral radius of A is limit norm A power n 1 by n that is also equals to infimum of norm a power n whole power 1 by n. Okay. So we have spectral radius of any element a power n is less than or equal to norm of the element. Now we know that by the spectral mapping theorem, spectrum of a power n is lambda n, where lambda is coming from the spectrum of a. So this implies that spectral radius of a power n is nothing but spectral radius of n. So therefore we can say that spectral radius of a power n is spectral radius of a power n less than norm a power n. So this implies spectral radius of a is less than or equal to norm a power n 1 by n. So on the left hand side it is a constant, whereas right hand side it is changing with n. So we can say that this is infimum over n norm a power n whole power 1 by n. So this is less than or equal to limit infimum of so let us call this inequality as 1. We want to claim that, so we want to show lim sup of norm a power n whole power 1 by n is less than or equal to spectral radius of a. Okay, so for this, so let us define set delta as set of all lambda in C such that mod lambda is strictly less than 1 by RA. Okay. Okay. So lambda is in delta. This implies spectral radius of a lambda a, that is nothing but mod lambda into spectral radius of a. This is strictly less than 1. So from this we can say that 1 is not in the spectrum of lambda a, or we can say that 1 minus lambda a is invertible. Now define a functional f from delta into C by f at lambda is phi of 1 minus lambda a whole inverse. This is true for, so let us take phi in a star, define this way for every lambda in delta. Now as in the case of the proof of spectrum is non-empty for a element in a Banach algebra, so we have defined such a function and have shown that it is entire. Now here we can easily show using the same proof, check that f is analytic in delta. So we have to use the same proof that we used earlier. Okay. Now if f is analytic, so we can represent it by a power series. So we can have f lambda can be written as some alpha n lambda a alpha n lambda n, n equal to 0 to infinity. See, for all lambda in delta. So let us call this as 2. Okay, now if mod lambda is strictly less than 1 by norm A, then we can say that norm of lambda A is strictly less than 1. Hence, we can say that 1 minus lambda A is invertible, and not only that, 1 minus lambda A inverse is given by the Neumann series. This is summation n equal to 0 to infinity lambda n A power n. So let us call this equation as 3. Okay. Now from 3 we can obtain that f lambda we can write as phi of 1 minus lambda A whole inverse. Since phi is a bounded functional, we can write this as summation n equal to 0 to infinity phi of lambda power n A n. So this is lambda n phi of A n. So let us call this as equation 4. We have bigger set. So this is 1 by RA. So 1 by norm A is less than 1 by RA. Now in the smaller disk we have representation like this given by 4, and inside a bigger disk we have representation given by 2. Since the power series representation for a function is unique, since it is analytic, so by the uniqueness of the power series, we get alpha n to be phi of A n for every n. That means we can represent f lambda summation n equal to 0 to infinity phi of A n into lambda n. Okay. Now we know that by 4 the series is convergent. So by 4 we can say that lambda n A n, so this goes to 0 as n goes to infinity. So since the series is convergent in 4, we can conclude that this is true. That means, so from this we can conclude that phi of lambda n A n is bounded So this implies lambda n A n, this is bounded by the earlier lemma. Hence there exists a constant m lambda such that norm of A power n lambda n is less than m lambda for every n. So this implies norm of A power n is less than m lambda divided by mod lambda power n. Okay, so if we take norm of A power n power 1 by n less than m lambda power 1 by n by mod lambda, and this is true for every lambda in delta. Now as n going to infinity, So we can take lim sup. So this exists and it is less than or equal to 1 by mod lambda for every lambda in delta. Okay. Now when lambda is in delta, so this implies lim sup of n tends to infinity norm a power n whole power 1 by n is less than infimum of 1 mod lambda, where lambda is coming from delta. So if lambda is coming from delta, this implies mod lambda is less than 1 by Ra. This implies 1 by mod lambda is bigger than 1 by Ra. So 1 by mod lambda bigger than Ra. So if you take infimum of all such things, we get that infimum to be Ra. So this is nothing but lim sup of norm a power n whole power 1 by n is nothing but less than or equal to Ra. Now earlier we have shown that Ra less than or equal to lim inf of norm a power n 1 by n. So this is inequality 5. So by 1 and 5 we get spectral radius of A is nothing but lim n tends to infinity norm a power n whole 1 by n. Because we have shown lim sup of norm a power n whole power 1 by n less than or equal to Ra, but Ra is less than or equal to lim infimum of norm a power n whole power 1 by n. But we know that lim infimum is less than or equal to lim sup, so we can conclude that lim inf and lim sup are same, hence the limit of the sequence exists. So this completes the proof of the spectral radius formula. Okay, now we have proved the spectral radius formula. Now using this we can actually get some important consequences. Suppose V is a isometry. Then we know that V power n is also isometry. For every n in n. So hence we can say that the spectral radius of V is lim n tends to infinity. This is now V power n or power 1 by n, but that is 1 all the time. Okay, but we also know that norm of V is always equals to 1. Okay, now let us take f in C of k, where this k is compact order space. Then we can say that spectral radius of f we have shown to be that spectral radius of f is norm of f. So this can be directly shown using the spectral radius formula also. So spectral radius of f so this is norm of f only, because norm of f power n is norm f whole power n. So let us look at One more example. Let T be a normal operator. Then we know that norm of T square is norm T whole square. So also T square is normal. So hence we can again using the same formula, norm T square square is norm T square square. So let us look at, so this is again, we can show that this is, so norm T power 4 is nothing but norm T whole power 4. In fact, we can show that norm T power 2 power k is norm T 2 power k for every k in n. Now by the spectral radius formula, spectral radius of T is nothing but limit norm T power n whole power 1 by n, but we can say that limit k tends to infinity norm T power 2k by 1 by 2 power k. So you will get this to be norm T only. So we got a subsequence of indices to power k such that limit of that is norm T. Hence we can conclude that spectral radius and norm T are same. Okay, so these are some of the important consequences of the spectral radius formula. In the next class, we will be discussing about some more important properties of spectrum. I will stop here. Thank you very much.